Physics is often described as an exact science, built on precise equations and careful measurements, but in real practice, physicists rarely deal with perfectly exact descriptions of nature. Instead, physics relies heavily on approximations, intentional simplifications of the real world. If the universe is endlessly complex, why do these simplified models work at all? And more importantly, why do they work so well across so many areas of science and engineering? In this video, we step back and look at the big picture behind approximations in physics. The physical world around us contains an enormous number of interacting variables. Objects are never perfectly smooth or uniform. Forces vary from moment to moment. Even something as simple as a falling object is affected by air motion, temperature, shape, and surface texture. Trying to include every detail would make any calculation impossible. Perfect accuracy is not just difficult, it is fundamentally out of reach. To understand complex systems, physicists begin by stripping them down to their essentials. Objects may be treated as point masses, surfaces as frictionless, and gases as ideal collections of particles. These assumptions are clearly not realistic descriptions of the world. Instead, they are tools that allow us to focus on the most important features of a system. Approximations are not made because physicists cannot do better mathematics. They are made because isolating the dominant effects leads to deeper understanding. By temporarily ignoring small influences, we can see which forces and relationships truly control the behavior of a system. Air resistance provides a clear example of how approximations are applied. For light objects or long fall times, air resistance dominates the motion. But for dense objects over short distances, its effect is small compared to gravity. Ignoring air resistance in these cases produces results that are close to reality while remaining easy to analyze. Many physical systems behave in a simple and predictable way when they are disturbed only slightly. Near equilibrium, complex forces often reduce to linear relationships. This is why pendulums, springs, and vibrations can often be described using very simple equations for small motions. One reason approximations work so well is that nature is generally smooth and stable. Small errors in assumptions usually produce small errors in results. Most physical systems resist dramatic changes, allowing simplified models to remain reliable across a wide range of conditions. Engineering design depends heavily on approximate models. Engineers understand the limitations of these models and compensate using safety factors and design margins. The fact that bridges stand, aircraft fly, and electronics function reliably is strong evidence that approximations capture essential physics. Approximations are never universal. At very high speeds, classical mechanics must be replaced by relativity. At very small scales, quantum mechanics becomes essential. Recognizing where approximations fail is just as important as knowing when they succeed. Physics builds understanding in layers. Simple models provide a foundation, and more advanced theories refine those ideas. New theories rarely discard old ones. Instead, they explain why earlier approximations worked within their limits and expand upon them. Approximations help us see patterns that would otherwise be hidden by complexity. They clarify cause and effect relationships and allow us to build physical intuition. Understanding often matters more than achieving extreme numerical precision. Physics advances by finding the right balance between complexity and simplicity. Approximations allow us to translate an infinitely detailed universe into ideas the human mind can grasp. They are not a weakness of physics. They are what make meaningful understanding possible. Thank you for watching.